Okay, so I think we can start the introduction. So we have two talks this morning. And I should say after the second talk at 10:30, we're going to try to take a photo outside. It's just right outside here. So if you're here, then please come on outside and then, get your photo taken. Okay, the first talk's by Magda Carr from Newcastle University, and this is internal solitary waves and their interaction with sea ice. Okay, Magda, go ahead. Thank you.
Okay, good morning, everybody. Thank you very much for the introduction, Henrik. I'd like to begin by thanking the organisers. It's a real pleasure to be here, so thank you very much for the invitation. So today we're going to be talking about internal solitary waves and their interaction with sea ice. So I'll begin by just explaining what internal waves are and say a little bit about their presence in the Arctic. I'm then going to talk you through the experimental methods that we've used to investigate this problem. I'll say a bit about the motion of floating surface particles and also a bit about the flow evolution under ice. So typically what we have throughout the world in our oceans is that the sun heats the near surface waters due to solar radiation. So the near surface waters are typically warmer and lighter than the deep waters. These two water bodies get separated by a density interface, which I'll refer to as the pycnocline or the thermocline. And that density interface can support internal wave motion in the same way as the interface between air and water supports surface wave motion. However, internal waves have very different properties, and this animation just gives you an idea of what they look like. Now, in the Arctic, the picture is a little bit different, as I'm sure most of you know. So typically what we have in the Arctic is that the near surface waters are colder and they're fresher than the deeper, warm, salty, deep waters. But again, we have a stably stratified water column, and between these two water bodies, there's a density interface where the density changes relatively quickly with depth, and we can get internal wave motion. And this animation just gives you an idea of the flow pattern associated with the internal wave motion. So today we're going to be asking questions about what happens if you have an ice edge at the surface. How does that affect the wave? How does the wave affect the ice edge? What might we expect to see? We're also going to be looking at what happens if you have some ice at the top. Does that ice get transported with the wave motion? And what happens at the underside of the ice? Okay, so we know from past studies that internal waves can cause flexure of sea ice, and theoretical studies have suggested that they may be the cause for the formation of ice bands in the marginal ice zone. However, field studies are very limited, or they certainly have been in the past, and it's only been very recent that we're beginning to build up a picture of what the internal wave field looks like in the Arctic. Okay, so due to the recent prolonged ice retreat and solar observations, we're starting to see more and more observations of high frequency internal solitary waves being widespread in the open water areas of the Arctic Ocean and its marginal seas. But this is relatively recent, only over the last 10 years or so. So these three images you see here are field observations. They're taken from a paper by Kozlov et al. In the White Sea. This first one is a SAR image. Okay, so we're looking from space on the surface of the sea. And if you look close, you can see these bands of light and dark regions. This is actually the surface signature of an internal wave field beneath. So what happens is, as an internal wave disturbs the pycnocline, it induces flow at the surface. That flow pattern has regions of convergence and divergence, so it causes regions of rough and slack water, and this can be picked up in satellite imagery as we see here. The second picture shows you the bathymetry in that region, and superimposed on the bathymetry are the observations that were made of these internal wave patterns. This third image is a CTD profile. So the color scheme you're looking at here represents temperature, and you can see the thermocline is being disturbed by an internal solitary wave train. So these waves travel as packets, they're rank ordered, and what we get, they self-order. So the leading wave is always the largest, because solitary waves have this nice property that the larger the amplitude, the faster the travel. So the biggest amplitude wave comes to the front, and so on. So if you were to let this to go for an infinite amount of time, you would see this leading wave just get away from the ones in the tail. Okay, so how do we model this in a laboratory? So we have a wave flume and we set the flume up so we have a stratification where the lower layer is salty and dense and the top layer is fresh and light. And we put a gate at the upstream end of the tank, and behind the gate we fill with fluid which is fresh, so it matches the fluid in this top layer. You can see that gives a density gradient across this gate, so that when we remove the gate, we get an internal salty wave of depression forming on the picnic line, and it propagates into the main section of the tank. At the downstream end of the tank, we're going to have some ice. It might be real ice or it might be weighted floats. I'll show you both. And we're going to look at the interaction between the ice and the wave. So this is just a time-lapse movie showing how we set the experiments up in the wave flume at Newcastle. So the flume's 7 meters long and it's 0.4 meters wide. And we begin by filling the dense brine layer. So that's what you can see happening just now. Once we've got that deep, dense brine layer into the tank, we have an array of sponges, which we sit on top of the water column, and we then very slowly drip feed fresher fluid from these reservoirs above the tank onto the top. So this forms our density stratification. Once that's complete in the main section of the tank, we have a gate, which we put in the upstream end, which you're not going to see in this particular movie. We fill behind the gate with that fresh fluid, and that gives us the density gradient to drive the wave. So everything you're going to see today is driven purely by buoyancy. There's no mechanical forcing. Sitting above the tank, we have these conductivity probes. We use them to take conductivity readings in the water column. As the salinity of the water changes, the conductivity readings change, and we can infer the density field. We also have beneath the tank a light box. It makes a thin column of light coming up through the tank, as you can see there. We seed the water column with neutrally buoyant tracer particles, and we're going to be viewing from the side. So here, this just gives you an idea of what the output's going to look like. So this first video is just what we see with the naked eye in the lab. So we've got these white tracer particles on a black background. The second video is just a false color scheme of that same video. And this third movie you see here is the output from something called PIV. So we can do PIV on these images. It uses a cross-correlating pattern matching technique to effectively trace where particles go from one frame to the next. And from those measurements, we're able to get the displacement field. And because we know the time interval between frames, we're able to compute the velocity field. So the arrows you see in this lower plot are the velocity vectors, and the background color scheme is vorticity. Okay, so the first experiments I'm going to show you took place at HSVA in Hamburg. This work was funded by Hydrolab Plus, and there were various people involved who I'll say more about in a second, but this work was done in a cold lab. So this blue basin you see here is the Arctic Environmental Test Basin. That's normally filled with water. For our experiments, the tank was drained and they purpose-built this small wave flume that you see sitting within the tank. We're sitting in a refrigeration unit. You see the corrugated lab on the inside. We had lots of kind of practical problems to overcome. So these little floating sponges that we used to do the stratification would often freeze, so we had to constantly keep them warm. This red structure you see here was the gate, and this big mess of blankets are actually the computers and the cameras. We needed to keep them warm, and you can see we had to construct this kind of gazebo above them, because if we raised the temperature in the lab too quickly, we made it rain. So there was lots of practical considerations that we had to get around. We only had 3 weeks of funding. We managed to do 2 weeks of experiments. So you're going to see the data set is somewhat limited in terms of the time we had, but we still got some interesting results. So the first thing we're going to consider is what happens if you have grease ice at the surface of the experiments. So to make the grease ice, we just got some model ice from the facility in HSVA, crushed it up in a bucket, so we got mushy, slushy ice, and then we slowly lowered it into the main water column using a grate. And if I can just play these two movies for you. So this one we're looking down on the top of the tank, and this one we're looking in from the side. And you'll see as the wave approaches, it transports the grease ice down the tank in the same direction as the wave. There was some water between the lumps of grease ice, and you can see that the grease ice got compressed by this motion. And I'll just let this movie play out. So what happens now is the wave hits the end of the tank, and it then comes back upstream. You can see it transports the grease ice back upstream again. And if you look closely on this image, you can see actually this picnic line actually feels the shape of the bottom of this ice. We get this kind of bump effect here due to that interaction. And also, if you look closely, there's some small scale disturbance at the underside of the ice due to the roughness of this ice interacting with the wave-induced flow. Okay, we also looked at nillus ice. So we formed this at the top of the experiment just by chilling the lab right down. So we made this in situ. So this is a thin sheet of ice. You can see we have some crystals growing down into the water column. This is just me seething underneath that ice. So in this case, the ice wasn't free to move. Okay, so it actually went right the way to the edge of the tank. So you're not going to see any transport of the ice. But if you look closely, we've got roughness at the underside of the ice. And you can see as the wave goes past, we get small scale vortices forming at the underside of the ice and turbulence generated there as a result. We also looked at level or sheet ice. So we looked at a thickness of 1 centimeter and 1 meter long. I'll show you that one first. So in this case, you can see the bottom of the ice is much smoother than in the previous two cases. And again, what you'll see as this wave approaches is that that ice is transported with the wave as it propagates down the tank. So here it comes. And you can see again quite clearly the ice is transported by the wave-induced flow at the surface. Okay, we also looked at a piece of level ice which was 6 centimeters thick. We looked at 1 meter in length and 2 meters in length. And I'm going to try and play all these three together. Okay, so in this case, because the ice is so thick, it actually protrudes it down into the picnic line, which is this region here. So this, in this case, you'll see there's interaction between the ice edge and the picnic line. Again, you'll see that the ice is transported, but notably in this case, if you look at the picnic line, you'll see that it gets distorted and it actually breaks. We get this overturning billow on the interface due to the interaction with that ice edge. Okay, so we're able to use those images to get wave measures and also ice measures. And we do it really simply using a time series analysis. So if we take a vertical column down a given image, and then we take that same vertical column for every timestamp in our movie and stack them left to right, we get a trace that looks like this. Okay, so you can see here that we can trace the wave shape. So from this, we can measure the wave amplitude, we can measure the wavelength. We can also get the time that the trough of the wave is at this location. We can do this at different locations and get different times for the trough and hence measure the wave speed. We can also measure the ice speed if we take a horizontal slice along the underside of the ice. Then in this region here, we just have black. So let me explain that again. Sorry, we're going to take a horizontal slice, flip it through 90 degrees, and then stack them left to right. So in this region here, we just see black, which is water. And where we start to go orangey red, that's the ice edge. The time code on these two plots is the same. So you can see in this region here, the ice is stationary before the wave approaches. And as the wave approaches, the ice edge is accelerated and it then reaches a constant speed before it hits the end of the tank. So in this region here, we can take the gradient of the line to get a measure of the ice speed. And here we're plotting ice speed divided by wave speed. And on the x-axis, we have the length of the ice divided by 2 times the wavelength. And this is just for the level ice cases. So we looked at 2 different thicknesses, 1 centimeter and 6 centimeters roughly, and 2 different lengths, 1 meter and 2 meters. We don't have a lot of observations, but the ones we do have collapse nicely onto this line. And it would look like for these relatively long flows, there is a linear relationship between the non-dimensional flow speed and the non-dimensional flow length. And the longer the flow, the slower it moved. The thickness of the flow did not appear to affect the wave speed for the range that we investigated. So now some results from the PIV. So in this image, the first row I'm showing you is horizontal velocity. This dashed line you see here marks the picnic line location. And this little blue line marks the underside of the ice. So we've got the grease case, the nillus case, and the level case. In the second row, the color scheme you see is vorticity. And you can see in the rougher cases, we have an enhanced vorticity signal at the underside of the ice. Whereas in the level case, that vorticity signal is a lot weaker. The third row is showing you log of the dissipation of turbulent kinetic energy. And the last row is the average dissipation. And we're plotting against depth. So what you can see in these plots actually is that the dissipation underneath the ice is comparable to that at the picnic line. And we found that in the grease case, 44% of the dissipation occurred underneath the ice. It was 39% in the nillus case and 35% in the level case. So the main conclusions from that kind of small set of experiments we did was that the interaction of internal solid waves with sea ice can lead to dissipation of energy through 3 different pathways. So we can have generation of vortices at the underside of the ice, transportation of the ice, and also deformation of the waveform. Now, one thing I do just need to point out is that in the laboratory, the buoyancy frequency was of the order 1 per second, where buoyancy frequency is the square root of -g over rho naught. Rho naught is just a reference density times the density gradient. And the Reynolds number in the lab was 10 to the 3, whereas in the field, it's more like 10 to the 6. Okay, so there are differences in these numbers. And in future, we need to vary these 2 parameters to see how we can infer our results for the field. What can we infer about the field? So this work was done with several people through the Hydrolab Plus scheme. We had a really good time. It was fantastic to get so many people together. So in the first week of the experiments, I was joined by Ilka Fur and Oyvind Teen from Bergen. And the second week, we had Atle Jensen from Oslo, Emilian Parot from UEA, and Jarle Bernsten from Bergen also. And in this third week, I was joined by Henrik Kalisch from Bergen and Peter Sutherland from Brest. We were supported by Andrea Haas and Kalle Evers at HSVA, and they were real experts on how to make ice and support us with the lab experiments. We have published this work in GRL, so if people want to read this in a little bit more detail, please feel free to look that up, or just contact me also if you have any questions. So typically this work kind of gave us more questions than what it did answers. So I've been looking at this problem in a little bit more depth with my PhD student, Samuel Harkin Evans. So Sam's in Newcastle with myself, and he's funded by the NERC One Planet studentship. And everything you're going to see now is Sam's work. And I must also give thanks and credit to Sam for the animations that you saw in the start of the presentation. They were also down to his hard work. So the experiments we've been doing in Newcastle are not in a cold lab. So we are using floats at the top of the water column to replicate the ice. And we weight them to give them a density which is comparable with sea ice. The density in the top of the water column also matches that which you'd expect in the ocean. The difference comes in the bottom layer, where we oversalt to ensure we can get good visualizations with the seeding that we have. So here you're seeing a view from the side at the bottom and a view from the top again. And what Sam's been doing, he's been using something called particle tracking velocimetry to get measurements of those floats at the top, so we can analyze their motion in a bit more detail than what we were able to in Hamburg. And Sam has been modeling this. He's come up with an equation of motion for the ice. So we can write the drag force on the ice as a half times the density times the relative velocity squared times some drag coefficient multiplied by the cross-sectional area. We can write acceleration as force divided by mass, and therefore get an expression for the acceleration of the ice. So this is an expression for the acceleration of the ice at some time t. We're going to use it to predict the velocity of the ice at a time step t plus 1, just by saying that the velocity of the ice at t plus 1 is the velocity of the ice at time t plus delta t times the acceleration of the ice at time t, where we have this expression for that acceleration. And we can do something similar with the displacement field. And here you can see how this compares to the lab. So here we're plotting position x, and this is time. The black line you see here is the lab measurement. So this is how we measure the float in the lab. So it wobbles about a little bit, but it's pretty much stationary before the wave comes along, and then it gets moved by the wave. The blue line you see is the fit. So this is from Sam's model. And if he chooses a drag coefficient, in this case of 17.5, you can see you can get excellent agreement between this very simple model he's come up with and also the lab measurement. Here I'm showing you those plots again, but the background color scheme here is the wave-induced horizontal velocity close to the surface, and this is measured by PIV. So here you can kind of relate the motion of the float to that of the wave-induced flow at the surface. So this work is preliminary. We've concentrated on single circular floats so far. We intend also to look at square floats, rectangular floats, and also a mixture of float sizes. So this all still needs to be done, but that's where we hope to head with this. This just gives you an idea of what happens if we have more than one float in the top of the water column. You can see that we get collisions, and also they rotate a little bit. As I say, we still need to analyze these experiments in more detail and do more. Just wanted to give you a rough idea of how they look. We've also been looking at interaction with ice in terms of the ice edge and the underside of the ice. So in this movie, if you just concentrate on the underside of the ice, you'll see that we get a vortex forming at that leading edge, and it seems to persist and travel along with the ice. In this case, that flow is very smooth, so we don't think the generation of that vortex is due to roughness. We think it's an edge effect, and we're yet to analyze that in more detail. But again, you can see it here in the PIV data. If you look at these vectors, you can see they're picking up that vortex at the underside of the ice. Okay, we spent a lot of time locked out of the lab during lockdown. So Sam's been delayed in terms of getting into the lab. So during that time, we actually had to go to some numerical work. And Sam's done a fantastic job getting to grips with this. The numerical method we've been using is something called SPINS. It's been developed by Kevin Lamb and Mark Statzner over a number of years. So SPINS solves the Navier-Stokes equation. So the first equation you see there is Navier-Stokes, and it just represents conservation of momentum. We also have the incompressibility condition and an equation for the density field. And we set up the numerical domain to mimic the laboratory. And we know from past studies that the two replicate one another really well. The main difference between the numerics in the lab is that the numeric has a rigid lid everywhere, so there is no open water in the numerical scheme. However, this just gives you an idea of some simulations we did with an MMath student last year. We have an ice edge, and we've pushed the picnic line right up to the underside of the ice, and you can see we get some really interesting dynamics going on. It's a bit like the experiment we saw in Hamburg, where we had interaction with the ice edge. The wave looks as if it's going to go unstable a bit. You can also see we've got entrainment of this deep lower layer fluid into the wave core. So again, lots more to do there, and we're excited to get going with that as soon as we get a bit more time. With that, I will end. Thank you very much for listening and for your attention, and I welcome any questions. I'll be staying online for the most of this morning as well. If people want to talk to me, or do please feel free to email me. Thank you for your time.
Thank you very much, Magda. Very nice talk. Thank you. Are there any questions? Just a second, it's all the way in the back. I have to go with the microphone. No problem. Yes.
Hi, Magda.
Hi.
I have a quick question about when you computed the drag coefficient in the experiments. Because we went a little bit quick. When you compute the force, the area that you consider is the frontal area of the floats or the underside area?
Yeah, thank you. That's a really good question. My understanding is it's the cross-sectional area, so looking down on the float, but we actually in the calculation absorb that into the drag coefficient. And then the drag coefficient is something that we're just using by trial and error to get a good fit. So we need to think a little bit more about exactly how that drag coefficient should be chosen.
Thank you. Any other questions? Yeah, go ahead.
Hey, Magda. In the first numerical simulations, you kind of showed some trailing waves, and then in the experiments, you were kind of explaining these trailing waves more to do with the effect of the ice on top. Did you not see any effect in the experiments of any trailing waves?
Okay, so you say in the first numerical simulation?
Yeah.
Let me just find that. Sorry. Oh, so these the animations right at the start.
Yes, exactly.
When we generated in the lab. Yeah, so what we have is when we generate these waves in the lab, we when we take the gate out, let me find it. Next one, I think. I've lost it. Sorry. So when we take the gate out, you'll see that there's a bit of a mess. So there's a sorting distance of about 1 meter before all that mess comes off due to the generation process. But then when we're looking at the point where the wave interacts with the ice, that trailing mess has basically sorted itself out. And typically what we have is just a clean solitary wave. And then we get the second wave in the train, which is much, much smaller. Okay, so that's typically what we see in the experiments. There is a little bit of discrepancy between the experiments and the numerical simulations, because obviously in the experiments we have this physical gate and there's a void gap that gets left there. Whereas in the numerics, we have a smooth tangent profile. So there is a little bit of discrepancy there in terms of that input signal. But by the time we are far downstream, it's normally clean.
Okay, any other questions? Okay, so let's thank the speaker again. Thank you, Magda. And